Hello Huskies, let's talk about functions. Functions are fun. Our objective for today is that we can identify functions and use function notation. The trick is that you've already actually been using function notation. Way back when we learned sequences, we talked about function notation. On your classwork, we did a fun little activity about the soda machine. Basically, if it's predictable, then it's working correctly. So you can use that activity to help you think about, is this a function, is it working properly, and we'll come back to that pretty much for the rest of the unit, but I'm not going to go into more detail today because we did a lot of that in class. So we have 5 different ways to represent a relationship, and on the back of your classwork it lists 4, but I'm going to add the 5th way as an equation. So the 5 different ways that we can represent a relationship in math are with a mapping, a table, ordered pairs, a graph, and an equation. So I'm going to show you examples for each of those, and we're going to show you, I'm going to have you learn what makes a function and what makes it not be a function, just kind of by looking at examples and non-examples. Before we do that, however, I need you to learn this concept. This is important. The domain is the set of x's that you use, and the range is the set of y's. And you could make up any song you want to help you remember that. It's something you're going to have to learn. I can't memorize it for you. So you can learn Y is the range, like to the YMCA song, that could help. Or you could sing to yourself, home, home on the range. Y is the range. Whatever. Learn. The domain is the x's and the range is the y's. Okay. So we talked about 5 different ways to show relationships in math, and some of those relationships are special and they're called functions. And to be a function, a relationship needs to have an input and an output, like the soda machines, right? We had an input and an output, and every input has exactly one output. Exactly one. That's what makes it a function. There are other relationships where inputs might have several outputs, but those would not be functions. So, you're going to need to pause the video in a second, and yes, I really want you to do it this way, and stare at this screen. Everything on the left is a function, and then we have the line down the middle of the page, and we have a couple of mappings where they are not functions. So I want you to pause the video and stare at it and see if you can decide what makes the stuff on the left a function and the stuff on the right not a function. Did you pause the video? Seriously, I need you to do it. Okay, so you've stared at the stuff on the left, stare at the stuff on the right. Now, if you notice everything on the left, I'm going to highlight a few things here. We have this mapping where 8 is being mapped to 6, 9 is going to 14, 10 to 10, 11 to 18, 12 to 14. We have associated every element in the domain with exactly one element in the range, and that is what makes this a function. The one underneath, again, we have every element in the domain is associated with exactly one element in the range. And then the same thing is happening down below, but look at down below. We have 1/4 being mapped to the square root of 13, and 0 is also being mapped to the square root of 13. And nothing is being mapped to the square root of 7. Is that okay? Well, it is, because to be a function, just to review this, every input has to have exactly one output. It doesn't say anything about if they all go to the same thing. And so look over on the right-hand side. We have an example on the top of something that is not a function. Check out 11. 11 is being associated with 6 and 14. This input, 11, has 2 outputs, 6 and 14. That means it's not a function. 12, the input, has 2 outputs, 14 and 18. Does that remind you of the soda machine, the day that it was broken? When you pressed a button and you got 2 different outputs. Okay, that's why that is not a function. Also, the mapping below is not a function because what is associated with 0? It's not going anywhere. Every element in the domain has to have exactly one element in the range associated with it. And this 0 does not have a place to go. It has no element in the range, so that is not a function. Okay, so everything on the left, again, is a function. Everything on the right, not a function. Pause the video for a second and see if you can figure out why the tables on the right are not functions. Okay, while you pause the video, I had a nice big yawn. Now we're going to come back and see why is this stuff on the left a function. Well, the x's are my domain, and everything in my domain has an element in the range associated with it. Same if I write the table horizontally instead of vertically. That doesn't really make any difference. But on the right, these are not functions because -1 is being associated with -11 right here. But down below, -1 is now going to -14. What? That's a broken soda machine. That -1 is going two different places. So that is not a function. And then look in the table below that's written horizontally. We have 1 repeated 3 times. It's going 3 different places. And that can't work. 2, yeah, going 2 different places. Not a function. Okay. Here's the third way that we can represent relationships, and that's with ordered pairs. You can just have a list of points. And that, again, we've got on the left is a function, on the right is not a function. What makes everything on the right not a function? Pause the video and stare at it for a second. Okay, welcome back. Everything on the left, we have the domain is all of those pink numbers, and the range is all of the numbers written in the second part of your point. And you can see that every element in my domain has something in the range. In other words, my domain is the list of 1, 2, 3, and 4. That's my domain for this one. And my range would be the second numbers, 1, 2, 3, 4. Let's see. I'll write those in green because they're in green. Oh, that's neon. Sorry, technical difficulties for a moment. Okay, here's my range, 1, 2, 3, and 4. So every element in my domain is mapped with something in the range. Well, let's look at the one below that. My domain would be 17, 18, and 19. And my range would be just 8. Is that a function? Can every one of these numbers be mapped onto 8? Yeah, that's okay. If you have a soda machine with 3 different buttons and they all give you the same drink, that's okay. Happens all the time. Faculty room, there's 3 Diet Coke buttons. They all give you the same drink. It's totally fine. So why are the ones on the right not a function? Well, you have 1, 2, 3. Oh, wait. I have 2 ones. 1 is going to 1, and then 1 is going to 3. So when we have that x that's being sent to 2 different places, that makes it not a function. And then, same down here. Oh, sorry, I didn't yawn enough. 8 is going to 2 different places, so it's not a function. Okay, what makes the graphs on the left a function and the graphs on the right not a function? Stop the video and stare at it for a minute, and then we'll come back and talk about it. Okay, can you answer that question? Why are the graphs on the left a function, but the graphs on the right are not a function? Do you notice anything that is consistent or the same in the graphs on the right? Well, now I want my neon green. When you're looking at graphs, you have something called the vertical line test. The vertical line test says that if you draw a vertical line anywhere through your function, it can only intercept your function in one place. And see these places where it intercepts my function? Yep, only in one place. So let's test down here. Vertical lines, yeah, I only intercept in one place. And here. Even though they're dots, that's okay. When I draw vertical lines, I'm only intercepting my function in one place. Well, let's test the ones on the right and see how they're different. When I draw vertical lines on this function, on this relation, I should say, I have intercepted my function 2 times. I have failed the vertical line test. Let's do it again for the ellipse. You can see that I'm going to be touching my function 2 times in several different places, all over the place, in fact. So this is not a function. think about the soda machine, the mappings, the tables, what we've been talking about so far. If this number right here, this is x, and that's like a 1, then what I'm saying is that 1 goes up here to like 3. It would be 1, 3, but it would also be 1, negative 2, right? You could go over 1, but then would you go up or down? I don't know. That's broken. It's not predictable and consistent. You wouldn't know what's going to come out when you press the button that says a 1 on it. So that is not a function. And then this last one, you could draw vertical lines all over here and not have a problem, but when you draw this particular vertical line, you're going through your function every single time, and that is not a function. Sorry, you're going through your relation. So that's what it looks like on a graph when it's not a function. Now I'm not going to spend too long on the equations. The equations on the left are functions. And things that you might be able to notice here, I have exponents on my x's, and that's a totally fine. Or I have x's without exponents, that's totally fine. I have y equals 5, that's a horizontal line. On the right, these ones that are not functions, what does the graph of this look like? Do you remember that's a vertical line? Is that going to pass the vertical line test? No. If I draw a vertical line through that, it's going to touch it in an infinite number of times. So that's not a function. And when I have an even exponent on my y's, that's what makes that not a function also. Because what I'm saying is that I might have something that is up here or down here, and again, it's going to fail my vertical line test. Okay, let's talk about something called function notation. You have already used function notation back when we did sequences, so this is going to kind of look familiar. But this is sort of why we have function notation. If I was trying to talk about a bunch of different equations, I'd say y equals 2x, y equals 3x plus 1, y equals 8, y equals 4x squared. How could I talk about these in a conversation? I would have to say, well, that first one has a coefficient of 2, but the second one has a coefficient of 3. And gosh, look at that third equation doesn't even have a variable. It just kind of gets confusing talking about these equations. And so one way to think of function notation is that I'm actually just giving them a name. And, you know, just like my name, Mrs. Bagley, I have a name that you call me by, and that helps differentiate between the other teachers at the school. So I could call these function, I'm going to call this first function the function f, and I'm going to call the second function g, and the third function h, and I'm going to go crazy and call that fourth function w. So those are the names of the functions, and then part of the name also is telling me what the variable is. What is the independent variable that we're using here? And so this would be f of x, g of x, h of x, and w of x. Now we have talked about this a lot back when we did sequences, right? We said f of x equals, and we did a bunch of sequences that way, exponential and linear functions when we were doing arithmetic and geometric sequences. So the function, the first one, f of x equals 2x, that is the name of my first function is f of x, and then the actual function is 2x. So the name of my second function is g of x, and the function is actually 3x plus 1. So if you zone out for a few minutes here and then come back, you're going to be super confused. Where did all these letters come from? But basically, all I'm telling you is that an alternative for writing y is writing f of x. Y equals f of x. So that's kind of an important concept to have down. And not only f of x, but g of x, h of x, p of x, w of x, whatever letter I want to use. But look at how convenient this is now. Now I can say, well, hey, look, the function f has a coefficient of 2. The function h has no variable, it's just constant. The function w has a coefficient of 4 and a degree of 2 because it has that exponent. Now you know exactly which one I'm talking about without me having to point or say the first or second one or whatever. So you can think of function notation kind of like that as just being a way to name a function, but basically it's just replacing y with f of x. Okay? All right. So then on your classwork, it says, what does f of x mean? I want you to remember and read this properly. This is f of x. This is not being multiplied together. This is not something that you can distribute or divide both sides by f. No, no, no. Just like my name, Mrs. Bagley, I get really upset when people call me Bag, of course. You can't just split my name up. My name is Bagley. So f of x, that's squished together. You can't split that up. Can't divide both sides by f. You can't distribute through there. That's the name. That is the name of the function f of x, or g of x. And so we're going to read the word of in between there. So, you know, you're used to seeing that. We have said that a lot back when we did the sequences. All right. At the bottom of your classwork, we have this problem. Don't get intimidated. Don't freak out by all the letters. I'm telling you, you have been doing this since like 5th or 6th grade. And I'm going to write an example of what you used to see, okay? You used to see a problem like this. It would say evaluate 3s minus 5 if s equals -2. And so you would say, oh, okay, I know what to do. I'm going to replace the s with -2, like this. And that would be 3 times -2, which is -6 minus 5. Oh, that's -11. And you would circle that, and that's your answer, and you're done. Okay, what we're doing now is doing this same exact problem, but I'm using function notation as a way of shortening my instructions or being more clear with my instructions. I could even say it's being more explicit. Haha, remember that? Okay, so using function notation, it says if g of s equals 3s minus 5, that is just telling me what is the expression to evaluate, 3s minus 5. Find g of -2. Now, back when we did sequences, we all the time we said f of x, f of x, f of x. We're used to seeing an x in here. You know, this is normally an x. So what I'm telling you is that x must equal -2. In other words, replace x with -2 or s with -2 and figure out what it is. Just like I did below, it's going to end up being 3 times -2 is -6 minus 5, which is -11. So in other words, I could say that g of -2 equals -11. And so just by saying this, g of -2, that's like using function notation as a shortcut for telling me all of this. So it's just being more efficient. You know, mathematicians, we like to be efficient. Okay, we're going to come up with a few more of those on your homework. Remember, you're just plugging in and evaluating. It's something you have done for years. Okay, I want to talk about a few problems on your homework. On the front, you'll have to decide, is this a function, yes or no? And you can use the stuff from the earlier part of the video to help you with that. So on your homework, number 13 says list the domain and list the range and decide if it's a function. So we always want to put our domain in brackets, in these big curly brackets. That's just a signal that's saying, hey, here comes the domain. So we're going to put in curly brackets a list of all the numbers that are in the domain. Domain is the x's. And so you're just basically going to list all the x values from the ordered pairs. Now, when I arrow them like that, you can see that 6 is actually used twice. We don't repeat in the domain. So my domain is just going to be 6, -4, 5, and 4. Yes, I know there was another 6, but we already wrote 6, and we're being efficient. Why would we write that twice? Now the range, why is the range? -1, 2, oh, I already have a 2, 6, and 5. That is my range. Now, is this a function, yes or no? Well, as I already pointed out, we have 6 going to -1, and then we have 6 going to 5. That's a broken soda machine. We're getting out 2 different sodas when we press the same button. So that is not a function. Okay? Now, number 14, we have to do the exact same thing. We have to list the domain and the range and decide if it's a function. So the domain is the list of all your x's. If the ones with the points are hard for you to see on the graph, then why don't you go ahead and write out all the points? That's not going to be a problem. Then it'll be a problem. It'll look just like number 13 did. Okay, so for 14, what are the list of points that we're using here? Give me all the coordinates. So there's, this one would be -3, 1, and we have negative 2, 2. We have negative 1, negative 2. And what else have we got? 2, 2, over 2, down 2, and what is that? 3, 1. So you could just list them out like that, and then it would be quite simple to just list as the domain all of the x coordinates. Negative 2, negative 1, 2, and 3. Remember, even if 2 is used twice, just write it once. And then your range is going to be all the y values. Y is the range. Got to get that memorized. Oh, I already used 2 and negative 2 and 1, so I am done. Is this a function? Well, you could just look and see if you're using in the ordered pairs any of the same x's going to different y's, but I want to refresh your memory on the vertical line test. One time, one time, one time. Oh, look, right there. I have gone through my function 2 times, so no, this is not a function because I have gone through it twice on my vertical line test. Okay, now this is getting a little bit trickier, and in class we used the domain finder. Remember my laser level to do this, and so this is what we're talking about right here when we say to list the domain. First of all, start with your curly bracket. Oh, that was a skilled one. Okay, curly bracket. Now I'm going to try to replicate my domain finder. Am I using any x's over here? No, 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 no. Beep. Okay, so when was I using x values in this domain? I started using x values, beep, right here when x equals negative 4. And so I began at negative 4, and then I was using all these x values in between, and I stopped at 5. And so I went from negative 4 to 5. That interval represents my domain. Okay, so I'm using all of the x's between negative 4 and 5, including negative 4 and 5. So those big fat dots on the end, it's kind of pretty obvious that it could be actually negative 4 and negative 5. I mean positive 5, that's why I have the equal to bar on there. So that interval, remember when we did compound inequalities? We're talking about all of the x's between negative 4 and 5 on the number line. Okay? Those are the x's that I'm using. Now, what is the range? Why is the range? So I'm going to turn my range finder horizontally, and I'm checking. Am I using any y's down here? No, no, no. Beep. Okay, so I am using all the y values. I'm starting the y values at negative 3, and I'm using all the y values until I get to 4. And so my range is between negative 3 and 4. Notice that I've put a y in there because y is the range. And I can actually equal negative 3 and 4, so I put the equal to bars on there. When you write those compound inequalities, always put your smallest number on the left. And it's always going to be less thans. It might be less than or equal to, but you're never going to use greater than signs because we're arranging these in order like on the number line. Smallest on the left, largest on the right. Hey, is this a function? Well, since it's a graph, let's use our vertical line test to check. It appears that I am only going through my function one time everywhere I draw these vertical lines. I'm not going through it more than once. So yes, this is a function. Yep. Okay. Number 16, let's talk domain. Domain. Oh, here comes the domain. If I was using my domain finder, when would I actually start beeping? These arrows mean it goes forever. So I'm actually using x's beep all the time. When am I not using an x? I don't know. So there's a couple different ways you can write this. You can say, well, I'm using all the x's on my number line, like all of them forever, both directions. So that is from negative infinity to infinity. That is the domain. And another way that we have talked about writing this is just by saying, oh, it's all the real numbers. Remember when you used the big fancy R? Or you could have even written out all real numbers. That's fine too. The domain is every single x you can ever think of. So a couple things about putting infinity into a compound inequality. Oh, gosh, I messed up on that. Let's fix it. I need another less than. Okay, that looks much better. So x is between negative infinity and infinity. Can you ever actually get to infinity? Is that a location? I'm sorry, Buzz Lightyear. When you say to infinity and beyond, there is no location that represents infinity. You can't be walking along and all of a sudden go, that's it, I've made it. Planting my flag, that's infinity. Nope, doesn't happen. Infinity is an idea that describes going on forever. So you can never actually get there. So you would never, ever put the equal to bar on infinity. Nope, don't do it. You can never actually get to infinity. Okay, so again, negative infinity is smaller than positive infinity, so that's why it's on the left. And what is our range? Okay, if you think about turning your rangefinder horizontally, am I using all the range values down here? Whoa, what the? I'm using all beep. I'm going to just keep using them forever. And so your range is going to be from negative infinity to infinity. That is your range. Put y. Y is the range. Is this a function? You betcha. It's just a line. All of our linear equations represent functions except for the vertical line where it's x equals a number. So, you know, if you want to use your vertical line test, oh yeah, you're good, you're good, you're good. Okay. I'm only going to talk about one more of these. I want you to try a few of these actually on your own. So, let's talk domain. Domain, all the list of x's you're using. Get out your domain finder, turn your pencil vertically, like x equals a number, and that is your domain finder. Are you using any x's over here? No, 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 no. Beep. Okay, I'm never going to stop. That arrow keeps going forever and ever. When did I start making the beeping sound? What x values was I using? Well, I started over here at -4, and I kept using all these x values, and then it just kept going forever and ever and ever and ever. So I'm going to write that as in a couple different ways. You could say -4 is less than or equal to x, which is less than infinity, to show that I started at -4 and then it just kept going to infinity. That's totally one way to write that. Again, notice I could equal -4 because of that big fat dot. That's telling me, yep, it does actually equal -4, but I can never equal infinity. -4 is smaller than infinity, so that's why it's set up that way. Another way to write this, though, is really, it's just all the numbers bigger than or equal to -4. So that's an alternate way that you could write that. If you don't want to be confused and you just always want to put the smaller number on the left, you always want to use less than, you want to talk about it as going to infinity, totally fine with what's in that first set of brackets. This is another domain that would be acceptable. Okay, range. Turn your pencil horizontally for your rangefinder. No, no, no. Beep. Okay, I'm not going forever here. When did I start using y values? I started using y values here, and I stopped using them right here. And what does that open circle tell me? Well, I could actually equal -1 because the big solid dot. So I'm going to say that y could actually equal -1, and then I went all the way up to 5, but not including 5. That's what that open circle means. I got all the way up, right up to using 5 as my range, but no, can't touch this. So that's why it's not less than or equal to 5, it's just less than 5. And I hope you see why there's no infinity, because it doesn't keep going. I am only using the y values in between this section right here. Comes down a little. No, it doesn't. Just kidding. That's my section that I'm using all those y values. Okay, is this a function? Well, when I do my vertical line test, I'm okay over here. But what happens exactly right here at -2? Well, my function was coming all the way up to 5, and then it jumps down, and at -2, it's exactly equal to 1. But that's okay because we had an open circle on the top and then the closed circle on the bottom. It makes this leap right here. That is still going to be a function. I don't have any problems with my vertical line test because this isn't actually a point up here. It's a point down there. It jumps down. Okay, I hope that helps you see what's a function, what's not a function, what's my domain, what's my range, and good luck with the rest of your homework.